So this question is asking which of the following statements is true. So option A, the spectrum of the convolution of a signal with itself. So that's like saying X convolved with X. Is the spectrum of that always the same as the original signal spectrum? So X of omega. Is that the case? Well, what do we know about the convolution property? We know that if you convolve in the time domain, it means you multiply in the frequency domain. So is that product always the same as the original spectrum? Well, sometimes it could be, but when you multiply two spectra, you don't expect to have the same spectrum. So the answer is no. So that's not true. And if you look down to option I, we have a very similar statement there. But this time it says it's never the same. Well, is that ever the case? Well, there must be cases when, yes, if you take a spectrum and you multiply it by itself, you get the same spectrum. So for example, if your spectrum looked something like that, then if you multiplied it by itself, then yes, the result could be the same. So always not correct, never not correct. So both I and A are excluded. The energy of a signal can only be calculated in the time domain. Okay, now if you remember Parsifal's theorem, it says that we can calculate the energy from x of t or x of omega, because it's the same signal. So because it says only, then it's false. So B can't be true. C, f of t is the integral. So f of t, that's your time domain signal, and that's your frequency domain signal. So what we're looking for here is the inverse Fourier transform. Now the inverse Fourier transform, there are two problems with it. There should be that minus sign shouldn't be there, and there should be a 1 over 2 pi factor here. So to make that true, you would need 1 over 2 pi there, and you'd need that to be positive. So C isn't true. D, the convolution of two signals is equivalent to the product of the two spectra. Yes, that's the convolution property. So that's true. E, here we have a time domain signal, here we have a frequency domain signal, so we're looking at the Fourier transform. So check that we have the right power, check we're integrating over time, check the limits of the integration. Yes, that looks correct to me. F, the Fourier transform of a Gaussian pulse is undefined. So what's the Fourier transform of a Gaussian pulse? It's actually not undefined, it's another Gaussian pulse. So that's not true. G, the inverse Fourier transform can be used to find the time domain representation of a signal f of t from its spectral representation f of omega. So let's just look at that. We're asking for inverse Fourier transform to find f of t from f of omega. So is that the inverse Fourier transform? Yes, that's exactly what the inverse Fourier transform does. H, convolution is the equivalent to the inverse Fourier transform. No, convolution is an operation, nothing to do with the inverse Fourier transform. So that isn't true. J, multiplying a signal by its Fourier transform is the same as carrying out an autocorrelation function. So multiplying by its Fourier transform, that means x times x, or x of t times x of omega. We would never do that. You would never multiply time domain and frequency domain. And certainly it has nothing to do with autocorrelation, so that's clearly not true. K, as the period of a periodic pulse train increases, as that goes up, what happens to the spectral lines? So as t naught goes up, clearly the frequency will go down, the fundamental frequency, so your spectral lines, will they get further apart or closer together? So clearly, as f naught decreases, then the spacing between these will become smaller. So they get closer together, not further apart. So this one is also false. So which of the following are true? There can be more than one answer. In this case, there are 3 answers. And that's the final answer.